Good morning, good evening. How are you all doing? Today we are going to be talking about belt tension. I've recently had a lot of conversations with Steve Builds, PF, maker of the tension tool. We all know Steve Builds, Thor, and from Thor on Discord. I think he's now part of the crew. And then CloakedWayne, the creator of the monolith gantry, and trying to figure out what the optimal tension is for all different types of motion systems, right? Is your motor a two-wheel drive, an all-wheel drive, a Y-assist, a whatever you motion system is, generally core XY at its core, and what, and also whether you have, upper shaft support on your motors. What should we be going for? Because currently the standard that Voron docs give us is 115 hertz. And for the longest time, no one really knew or wasn't really clear what that is. And PF has done a lot of testing on this, and he's found out that this is kind of on his meter reading, what it is, and that means that we're in this range here. We're a little bit low of that, but somewhere around here. He missed the 2.2 there. We'll have to talk about that. But we're about 8.9 to around 14 newtons or pounds of force of tension on our belts. And that's kind of the spec. So this 115 hertz is equal to 8.9 roughly. We'll do approximate 8.9 to say 14 newtons or pounds of force. So that's the standard, and where are we getting this standard from? And took a lot of discussions, but we're getting it from the motors. Let me clear all this out. We're getting it from the motors themselves. We'll get into this chart to calculate it. These are from PF Sense, so these are all PF here. This right here is from the Gates manual. It's like a 200-page, 100 and some page behemoth. We'll get to what that tells us too. So, looking at our motors here, we notice that this motor shaft is made of aluminum, and it can handle so much force, or newtons, or pounds of force. It says pounds, but it's pounds of force. The lower we go on the shaft, the more it can handle. The higher up on the shaft, the less it can handle. We are using both sides. So we have, I think it's the B belt here, up here, and we have the A belt here. We can't have the A belt and B belt at different tensions, as many of you know, because we'll get belt induced racking. The belts will, if we have our gantry here, and this is our X axis, if we start making, say, A tighter, right? A's here, we make that tighter, and we keep B at its standard, we're going to get something like this. It's going to pull that way. And that's because of the different force. If we were to follow this and do that, we'd have different force. So what we need is A tension equal to B tension. Based on that, we are limited to this on a standard two-wheel drive with no top support on the bearing. This is what we're limited to, right here. So what does that tell us? Right. Well, that tells us that the 115 hertz, that standard, is basically geared towards this. And it's taken a while to figure this out and to go through and have lots of conversations with people. But this is where we're at. What happened there? Where'd my... It's still there? Let's see here. Still there. Okay. Still there. Just, I don't know what I'm doing right now. All right. So let's get the thing back here. So this is where we're at. This is our max right here. Our max in a standard two-wheel drive based upon the force that the motor shaft can handle before it starts to bend. And when it bends, that's no bueno. I'm sure you guys have seen it when you looking down at your motor. Instead of the motor doing a perfect circle, it's doing one of these things. It's starting to go elliptical on you. that means your shaft's probably, most likely, your shaft is bent, and you've overdone its static tension. You just pulled it too much. You're too tight. So if we look at this, PF has done a lot of testing, and he said a good range of values is 1.8 to 2.2. If we come down here to his chart, right, his 2.2, this is his chart. This is the tension meter here. So 1.8 to 2.2, we're about 8.9 to roughly approximately 14 newtons. So if we're at 2.2, we're basically at this max, which is this is 2.2, and then this is 1.8. So to get us there, 2.0 gives us plenty of room where we're not at the lower end, but we're not maxing out the motor shaft. So this is where these numbers are coming from, and both of this is about 115 hertz. And we'll see that this one here is actually closer to 110, and this one is closer to 115, or actually the 2.2 is, but we'll get into that. We'll run the numbers in the actual calculator. So what is the max, though, that the belt can handle? Okay, that's the next question, right? Like, okay, I understand the motors, but what's my max that my belt can handle? Well, that's taken from Gates themselves. And this is the power grip long length belt specification. And this depends on the number of grooves in your motor pulley, which I don't know why yet. Still figuring that out, but we think it has to do with when you have a belt, all right? So this is your belt, and then these are your teeth. Let's just say it's like this, right? These are very good teeth. They're very artistically drawn. So what you see is you have a lot of material. You have a lot of material here, but you don't have so much material here. And we think that these numbers are based upon how much this is spread out across the entire belt. And as you can see, the more teeth you have, the more tension you can apply to that belt. So we're thinking the less amount of teeth, the more likely you are to stretch this here at where the teeth begin, and it could potentially break on you. So knowing that, let's take a look. We're at 20 teeth, so we're right here. Generally, I think we have 20 teeth, so we're in the middle. So, erring on the side of caution, for 6mm belts, our max tension is 6 newtons, or 6 pounds of force. So that's 6 pounds of force for 6mm belts, and for 9mm belts, it's 9 pounds of force. We go back to PF's table here. We see we'll use blue. We'll see that it only goes up to 6 pounds of force. So that's at a reading of, I'll make this here, a reading of 2.8 on his tension meter gets us 6 pounds of force. But what do we do if we have 9mm belts? And this becomes the problem. PF has run several tests, and what he has found is that if he starts going up on that tension meter higher than his max value that it currently is, what happens is it's so much force, the meter itself exerts so much force in the belt that it throws off the results. Now, he is looking into potentially coming up with another solution. I think one of the solutions is possibly attaching 2 tension meters at the same time to go up that, but it ends up being that taking the measurement throws off the measurement. So we could do things like we could use the sonic meter from Gates themselves, which is a very high precision, effectively an app again. We're going back to the apps, but it's a higher precision calibrated to measure the belts based on the vibration. We could do that. We could go back to the old style. Or what we could say is, okay, I know my 9mm belts can do 9 pounds of force. I'm going to leave it at 6. I'm going to put it at 6, knowing that I have wiggle room. Because as you approach these numbers here, right, you're basically hitting the limit of the belt. And the negatives of that are you're going to wear the belt out faster. Effectively, you've stretched out the rubber of the belt, the rubber material of the belt itself, that now you're basically relying upon the fiberglass inside to hold its integrity. So, yes, these are the max belts for our systems, the max tensions for 9 and 6 and GT2s. They do have another chart for GT3. I believe it goes up just a slightly bit higher. And of course, EPDMs have a different ranking also. But these are the max that Gates recommends. And of course, you can go like maybe 6.1 here, right? Because that's between 18 and 24 teeth on the pulley, or 9.2 or 9.1. But it looks like, based upon not having a supported motor, or based upon this is our max. So where does this lead us? This leads us to the discussion now. So we know, let me back up here. I know I'm going all over the place, but back up here. We know on an unsupported motor, this is our max, no matter what. So that's where we're at. But what about when we support this motor, right? Let's say we have the long boy motor shafts which come up, and we support it. What is our max at that point? My argument is it's going to be closer to this bottom one, because this bottom one is really supported here. And so if we go over this 7.5 pounds of force on the bottom, then we're going to bend the shaft. But we have a support here. So are we going to bend the shaft now this way? Right? Because before, this is before we were bending the shaft this way, right? It was just pulling straight like this. But now we've got it supported, but it's still aluminum. It still has a max give before it bends. And I'm thinking it's going to be the 7.5 pounds of force. Now, we might be able to get the 9, and I know some guys do go up to 9. So maybe, right? Maybe we can do 7.5 as a safety margin, and then 9 as the max, right? And that's based on this number here, based on our Gates data. So if we do 7.5 newtons, I'm sorry, 7.5 pounds of force, 29 newtons, we're still off this chart. But what is that in frequency? So we're going to do all these numbers here. 7.5 pounds, which is 29 newtons, and 6 pounds is 26.7, and then 9 pounds. Oh, what is 9 pounds? I don't know. We'll figure that out on the chart. All right, so that's kind of the overview on this belt tension. So what should you? We'll get to the conclusions after, but let's switch to the chart. So I have this Excel sheet here. It's the MP belt tension calculator. I don't know who made it. If someone knows who made it, please tell me, and I can give them credit. I'm going to post this on my GitHub. I'll include the link below in the description of the thing. I've added PF Makes drawings in here. Put a little credit to him. But what does this allow us to do? This allows us to calculate the belt tension. And it has different belt data. So there's a tab called belt data. And in it, we have all these belts, EPDMs, rubber, right, different widths, and it gives us a static tension, the linear, all the variables we need. So what do we need to do here? Well, we just type in GT2. We take the name for whatever name we're doing. Then we add the belt width. So let's say we have 6 and 9. And this tension is in pounds of force. And I included this so that we can see it. But we know that's 6 pounds of force, and then this is a max of 9 pounds of force, and it gives us the frequency in return. So if we want to use those app meters, we can use those app meters. So if we look, these are our max. So either one, the 6 millimeter or the 9 millimeter belt at 75% tension, which is a good safety margin, gives us 189.5 of that. If we want to do 100 of the tension, Doesn't look like it's. I don't know if that's working here. Let's see. 4. Tension. Tension. I don't think this one is in any of the calculations. C9. I don't see a C4. Do you guys see a C4? Nope. So this number doesn't actually factor in because we can hit 0 and it ain't going to change anything. Oh, it changes the EPDM too. What? I'm learning with you guys, so now we're going to look and see what changed. E6. Let's go back to 0. What number changed? All these changed. Okay. Well, I guess the calculator's slightly broken, but let's see if we can't fix it. Okay, we fixed it. So, all right, at 100 things of tension, 100% of the belt tension, we should just be able to change. Oh, that's why I messed with this. All right, so it says 100% of your belt tension is 12, but we know that's not the case based on our system. We know the 100% for the number of pulleys is 9. 12 is not there. So it might be the ultimate, like if I just pull it real tight, it's going to break at that point. But we know that's not the case. So we know the max tension here is 6 and 9 based upon Gates' own data. So if we look at it, at 6 and 9 at the max tension, they're both going to read the same frequency, which is 189 hertz. And we'll make this easy on us. Right? And at the 6, if we put 1.8 in on the tension meter, which is 2 pounds of force, 2 pounds of tension, we're at 110. And if we put the 2.2 in, which he does not have, but we're going to assume it's 14. So we'll say that's 14 newtons. So let's say it's 3.3. Nope, too high. 3.3 pounds. Oh, good God. Let's see, 2.2. So it's 3.3. Okay, so 3.3. We're at 140 hertz. We want 115. Oh, let's say 2.0. 2.0 gives us 110. Wait, oh, good God, I'm messing things up here. 2.5. So 2.5 is a little high. So we're at 122 hertz. So that's 2.5 is 2.0 on the meter. We're doing 3 things at once. So let me see if I can. This video is going to be all over the place. But we have the meter on the reading, and 2.0 gets us 2.5 pounds of force and 11.1 newtons. Okay, if we put the pounds of force, which this uses, in there, 2.5, we get a frequency of 122 hertz. To get the, let's say 2.25. Okay, so 2.25 gets us the 115 hertz kind of standard Voron measurement. Yeah, you're not going to get 2.2. That's going to be like 1.9 on the tension meter. Will get you exactly that, which will get you the, so right here, this value here, this 11.1 Newton force is a Voron standard. We can go a little higher, and then what I do is 3. So I'm at 100, is that 3? Yeah, because I'm at 2.0. So I'm at 2.5. So my frequency on most of my belts is 122 hertz. If we apply that same tension to the 9mm belts, our frequency is only 99. So to get the 9mm belts up to the Voron standard, because that's what most people are going to do, they're going to see the documentation, they're going to go 115, we are at roughly 3.5 pounds of force. So this has kind of been an issue with the belts, right? We've only known the frequency, when really what we should be looking at is this newtons, the force that the motors can handle as being our limiting factor. And at 3.4 pounds, right, we're about 2.2. Right, so if we get on the regular ones, if we go to 2.2, right, because that's how many pounds of force we can go. On a regular Voron, it's 115 hertz. And that's, oh, I'm using the wrong numbers again. 3.4. Right? 3.4. I'm confusing this thing again here. We have 3.4 pounds of force as the maximum. So the maximum is 142.2 hertz on 6, and on the 9s it's 116 hertz. So if you got GT9, you have the 9mm GT2 belts, and you're at 115 hertz on your tensioning it, you are really close to bending your motor. Really close. You should be a lot lower than that, right? So if we go back to the proper tension, let's say 3.4 is the max, but we're going to do, say 2.0, that's 2.5. You should be at 100 hertz. The other negative, the other thing that we've discovered, here we go, we got some more things, right? That, let me just see if I can clear all this out. I cannot clear it all out. Not most of us are using plastic parts. So another thing that happens that's not captured in any of this data is, let me see if I can just do another graph. Let's just get this here. Here. We'll go to another one. All right. So another thing that's not captured in this data is the effect on the belt tension on the plastic parts. Because we have a plastic part here, right? Let's just do like this. And then we have another plastic part on top of that. And then the motor is sandwiched between these two like this. All right, so these are our screws. It's once again, lovely drawings. They will be on sale at your local gallery. So we have our little gear here, right? Well, as I apply, let me get to purple. As I apply more tension this way, I am pulling this whole motor assembly this way. So this, I'm getting tension here, right? So this screw here is getting tension, and then this screw is coming this way because I'm pulling it, right? So you got to imagine like when you pull a door or you open up a can. Imagine opening up a can of soup, and you have it's the same basic principle, right? I have my can of soup, and the lid with the tab goes like this. Well, it's the same thing that's happening, except the lid's not doing this. The motor is. So as you approach your maximum, not only do we have the maximum that the motor shaft can handle, we also have the maximum that these plastic parts can handle without doing this kind of shape. So if we imagine this and we translate this to the plastic parts, we have our plastic parts here, and our motor is doing that. Oh, let me get rid of this. And this is what our motor is doing. Obviously, it's exaggerated, but this is what's happening. And it's happening because you're not going to see this gap. What's going to happen is this plastic here is going to get squished, and you might start seeing a little gap here. But as the motor moves now, you're going to get some wobble in it. And then you're going to get VFAs. You're going to get belts being riding up. So we have our flange, right? Got our flange. This is our pulley, whatever. And then this is our belt coming through. And this thing's going to wobble. And while it wobbles, this belt is either going to move up or it's going to move down. And then this right here is going to shear off our belt. You're going to start seeing rubber and all this other stuff all over the place in the back. And you're going to go, what the hell is happening? Well, you could have your tension too tight that is doing this soup can top thing here. So based upon all this, right, we don't want to approach these maximums. Because no one has done the testing yet to say how much can this plastic part hold? Can it hold this much force? And if someone's done the testing, I haven't seen it. So the Voron standard appears to be the 115 hertz over 200 over 150 millimeters for the gantry seems to be a good area to do to prevent all this negative stuff I've been talking about. And that 115 hertz, let's see, 2 pounds of force, 2.3, 2.2. So it's 2.2 pounds of force, which puts us about 1.9 on the tension meter. So if you go to, let's just make this a 6, and let's say 2.5. If you go to 2.2 on the tension meter, you're going to be, I'm sorry, see that's screwing me up too. 1.9 on the tension meter. Let me write this here. 1.9 on the tension meter is 115 hertz. Now, there's plus or minuses here. 2.0 on the tension meter is 122 hertz. These numbers are probably where you want to be. You're going to be in the lower end of you're going to be at spec or a little bit above, but you're on the lower end of what the belts can do and the shaft can do. And that's probably for the best because no one that I know of has factored in the plastic. Now, that brings up the next question, right? Should I go CNC? CNC, we all know you're going to get you can tighten that thing up more, and you can tighten it up to the tension that the shaft can handle, unsupported. Now we're still talking unsupported, because your chances of getting this soup can issue is less because you've got the metal is going to be able to resist this force here from the motors better. You might want to add some washers because you know that the M3 screws that we use for the motors have very tiny heads. You put a washer on, or you use one of those fancy ones, those, you know what I'm talking about, the conical ones, right? They look like this. And then the screw sits real nicely flush. They're going to spread out the force, the pulling force on the CNC parts better than just a screw head alone. You're going to get, this much area instead of this much area. So put a washer in it, and then you can go up to the max force that this says, 3.4 pounds. If we put 3.4, you're at 142 hertz, 3.4 pounds. It's still not that high, guys. It's about 2.2. 2.2. So CNC parts, we go up a little bit more, but now we're still maxing out this shaft. So what's the next step? The next step is to support it. So get one of those top supports where you put a bearing up top and you got a plastic piece. There you're going to probably jump all the way from 3.4. I'm guessing, we haven't done the data yet, we haven't done the testing, but I'm guessing you're going to be able to hit the 7.5 because that's going to prevent that bowing if you get below that. Well, at 7.5 for a 6 millimeter belt, let's go back to our handy dandy charts because we love them so much. You're over the working tension of that belt. So for a 6 millimeter belt, even with top support, you have a chance of actually just breaking the belt or wearing it out real quick. So what do? If you want to max out your motors maximum, so what was the 6? It was 6 pounds of force. So for 189 hertz, that's the maximum that belt can do. And you're going to want to give yourself some leeway. So if we give ourselves 10% leeway, that brings us to 5.4. 179 hertz, 5.4 is about 2.6, 2.7 on the tension meter. That would be the max I would do with double shearing. 9mm belts. Our max, if we go back to this, I might actually have to include this other sheet in here. You know what I'll do? I'll do that just to make it easier for you guys to see this data. I'm going to include this on that sheet when I post it. But a 9mm belt, roughly where we're at is 9.0. So 9.0, right? We're at 9. We're well over this. Where we even double sheared, I think we're over it. So if we say, let's just 7.75, 175 hertz. So our hertz, no matter what, if we're going to do these belts supported, they're going to come out to the same frequency. We're well outside of this tension meter range. That's going to be apps, unfortunately, or the Gates sonic testing meter. So can we go higher than that, though, right? I mean, the belts can go up to 9. Let's say this is GT2. We'll delete that. Oh, we will say that this is 9. So the belts can go up to 9 in that situation for, I'm sorry, this is a 9mm belt. But we're limiting it to this. Can this motor shaft, the next question is, can this motor shaft support 9 pounds of force? I don't know. We have, once again, no one's done that testing. We have a lot of empirical data, or a lot of anecdotal data, where people said, yeah, I've measured, I've tensioned it that high, but no one is really, that I know of, has really looked at all the different variables in that. Like, okay, great, you got it. What speeds were you doing? Were you maintaining that speed, right? Because the whole goal of extra tension is to get faster accelerations and potentially faster speeds. Generally, it's going to be accelerations. Well, are they actually using the machine consistently at that the higher acceleration? We don't know. I mean, you can set it in your perimeter in your slicer to go, 150, 1,000 millimeters per second squared, but we all know based on the model, the slicer is going to slow it down. So I don't know of anyone that's really done the test. I think VZBot maybe potentially 24/7 has, but I haven't seen the raw data or to lend me to that, say like, yeah, go ahead, we can go above this 7.5. And I haven't seen the data showing me what the max is, right? If we double shear this thing, we put a support up here, we got this bearing the motor, what's going to break, what's going to fail first? Is this aluminum just going to bend on me if I go up to, say, 10 pounds? 12 pounds, right? We know the motors will break at 9, or the belts will rated for 9. Can this shaft handle that, even double supported? I don't know. And what if I got long boys on it, right? Because that we have all these different variables that I haven't seen anyone do. So if we just do it, no, we're not going to save this. So we have a motor here, right? And that the data I was showing before was for just a regular motor, a short motor. And it was 7.5, right? Now let's say I got a long boy motor. Well, if I double shear it or add the extra support here, let me get a different color. Double here. I know at least I'm going to get to 7.5. I really don't know what the max is when this thing's going to fail on me, but I know it's going to be 7.5. With the double shear, or sorry, the long boy motor, if I put it up here, all right, I'm not going to get 7.5 because while I got this longer area to bend. But if I put it down here, or maybe a little bit higher, is it the same? I don't know. I don't know. And so there's a lot of questions that I don't know the answers to because I don't think anyone's done the testing on it. And I know I haven't done the testing. I have long boys, but I haven't installed them yet. So, long story long in all of this, where does this leave us? I think a good place to be is to be on these charts, knowing that the working tension in pounds force for your belt for the pulleys that we use. This is all for 20 for 20-tooth pulleys, right? We're right here. I think this is a safe spot to say this is the max belt tension I can do. And then we look here at the motors and we say, okay, I know for unsupported I'm here at 3.4 pounds of force as the max tension I can do. And then for supported motors, 7.5 is the max I can do. Which means for 6mm belts, the belt is going to be your limiting factor. For 9mm belts, the motor is going to be your limiting factor. And so that's where I think we are with this tension meter. This thing will help us if you want to get the frequencies that you need. Once again, I'll post this up. But I think the current standard, born standard of 115 hertz over 150 millimeters is a pretty good standard, and it gets us around here. Right? It gets us in what PF says. Right? He's actually done the empirical testing to do this, and I believe his numbers. So I think this is a good area to be. 2.0 doesn't seem unreasonable, right? We know 2.0 is closer to 122 hertz, so maybe 122 hertz should be the Voron standard, but I don't, that's not my call. But I would say that's pretty a safe bet to be because you're in this and you're not really quite, if you're at the higher end, you're skimming this number, but if not, you're pretty good. You're right around the middle, so yeah, 122 hertz should be good. For all the other belt tensions, if you go above 6.6 pounds of force, which means if you're doing 9mm belts with supported motors, you are back at apps or sonic meter. So I hope this is helpful, and I hope I wasn't too scatterbrained in explaining this to you guys. And when you make depending upon the motion system you have, you can get the correct tension without screwing up your motors or screwing up your plastic parts, and without approaching the limits of your belts and all that stuff. So I hope this was helpful, and maybe we can do some more testing as a community to figure out, okay, what's the result? Like, what are the good enough, right? Because we all know that we can, or most of us have this problem, that we keep going and we get diminishing returns, right? So if I'm at 9 pounds of force on a 9mm belt, is it really better than 6 pounds of force on a 9mm belt? Am I getting a noticeable difference in my prints, or can I just claim that I can go faster? Because there's two. Looks like there's becoming two schools, right? I want to go fast, and quality becomes secondary, or I want to go fast enough and get the good quality. But if I have to choose, quality's better. All right, so it's quality over speed, and I think that's where you have to decide where you lie. Do you want to be the speed benchy champion and max out all these numbers, or do you want to give yourself some, margin of error to just do good prints, but at the fastest speed that you're comfortable with and that you're not going to wear out your parts or your belts? So there's a lot to think about here, and your feedback in the comments is appreciated. Maybe I'll do a second one based on your feedbacks, but I just wanted to share this information with you guys so that, we're all kind of on the same page and we all kind of understand the subject that, at least for me, was kind of like, I don't know, I'll just do it that. It's just what it says. So hopefully we all get a little bit better understanding. And with that, I say good evening, good morning to you, and have a good one.